So, welcome everybody, and thanks for joining our Helios Nexensos webinar today, Strengths of PT RTDs, Key Properties and Their Advantages in Our Application. My name is Lisa Bürke. I am responsible for the marketing and communication activities at Nexensos today, and I will support the team in regard to your questions. Before we start, a few general information up front. The webinar is planned to have a duration of 1 hour, which includes Q&A session afterwards. So please note our session today will be recorded and used for internal trainings. The record will also be available for you afterwards. Regarding the settings, all attendees are muted by default. If you have any questions, please address them in the chat box you can find on the right-hand side. The questions in the box will be managed from my end and included into the presentation directly or collected for the open discussion round afterwards. Due to data protection policy, we are not allowed to address any specific individuals to keep you anonymous. If there are any detailed questions, please come back to us afterwards via mail or phone. Also, please make sure that your audio works. Our recommendation is using the headset. Another option is to dial in via phone. You receive the according numbers by invitation mail. So our speakers for today are Mrs. Charlotte Klemen from our application engineering team, mainly responsible for technical trainings and technical support for our customers, and Mr. Andreas Schreiber, who holds the position of Head of Product Management and Marketing. And now, thanks for joining. I hand over to my colleagues to start the webinar.
All right, thank you, Lisa, and a warm welcome to all of you. Let's start with the webinar. We have several chapters. We start with general characteristics of RTDs and their strengths. After that, we will talk about applications and the PT advantages. We will inform you about our products and key properties. And last but not least, we will talk about selection criteria and customization options before we allow you questions and give answers. All right. Good. On this page here, you see our product portfolio. We at Nexensos are proud to cover the full range from minus almost 200 degrees C to plus 1000 degree. And especially for the high temperature, we are leading in technology. Today, we will put a focus on some of the basic properties of RTDs. We will show you a comparison to NTCs, for example, and give you guidance for product selection. We hope you enjoy being with us, and I now hand over to Charlotte.
Yes, all right. Thank you, Andreas, and also thank you, Lisa, for the introduction. Andreas, could you? Thank you. All right, so if you want to talk about the characteristics and strength of PT RTDs, you need to compare them with other technologies. And the two sensor technologies that probably come first into mind, on the one hand, on the left shown PT RTDs, and on the right shown the NTC thermistors. And yeah, I would like to have a closer look on these two technologies now, so that you can really understand in the next step in which applications and why platinum temperatures are used. In really general, both technologies work with the same principle, and they detect the temperature via a voltage drop. So let's start with the on the left shown PT RTDs, which stands for Platinum Resistance Temperature Detector. So in most cases, platinum is the material to be for this technology, but also other materials such as copper or also nickel alloys are also conceivable. If we have a closer look in that schematic drawing here on the top, we can see I want to call it a sandwich system. And the center here is formed by our meander. And the meander is applied using the thin film technology, and it's then here covered and protected with different layers of glass. Now let's jump over to the right side. The structure of the NTC thermistor is a bit simpler. We have typically a bulk resistor, which is made of semiconductor ceramics. And the typical configurations of both technologies are quite comparable. So we have chips with lead wires, for example, or SMD types, also other electronic components such as SOT and TO types that are offered by Heraeus are possible. And the diode package here, for example, is a quite typical configuration for NTCs. Here, this graph on the next slide is really a rough characteristic curve, which means the resistance temperature dependence of both technologies. So the orange characteristic curve represents the PT-RTD, and the blue one is the NTC thermistor. And we can see directly that the platinum provides a positive and a linear characteristic, whereas the semiconductor for the NTC thermistor has a nonlinear and a negative resistance temperature dependence. The so-called TCR, which stands for temperature coefficient of resistance, is it's the average resistance change between a 0 degrees Celsius and 100 degrees Celsius. And a typical and also a standardized value for our RTD is the TCR 3850 ppm per Kelvin, and it's a material constant of the meander. But here also other TCRs can be created through I want to call it a target pollution of the platinum. The typical resistance values for the PT elements are 100, 500, and 1000 ohms. And these values refer to 0 degrees Celsius. On the other hand, typical resistance values for NTCs are much higher, with typically 10,000 ohms and higher. And that's quite important to know. NTC manufacturers specify those values for the temperature of 25 degrees Celsius, unlike our PT elements. An enormously important aspect is that the properties of the PTs are internationally standardized in the so-called DIN EN 60751. And this standardization helps to ensure quality, it guarantees safety, and it also ensures interchangeability for you as a user. Yes, here the next slide shows the most important properties in which those two technologies differ. Just the most important ones, because my target is here to give you only a rough overview so that you can understand in the next step what Andreas is going to tell you. But let's start here with the first point, the operating temperature range. PT sensors can be used in a much more extreme temperature range due to the material properties. So with our sensors, temperature ranges from almost minus 200 degrees Celsius up to 1000 degrees Celsius are possible. And the operating temperature range for NTCs is much smaller and ranges from minus 100 degrees Celsius to 300 degrees Celsius. But there are also some special types that have a temperature range up to 750 degrees Celsius. The next point, we could already see the slide before actually. The NTC has a very high resolution and consequently a strong slope of the characteristic curve, especially for low temperatures. So in that range here. And the PT, on the other hand, has a constant resolution. And this resolution varies from sensor type to sensor type. So a PT1000, for example, or even a PT10000, which are also available, have a higher resolution compared to a PT100 element. Talking now about the accuracy of both technologies, actually both technologies provide a very accurate measurement result. The difference is here that the platinum temperature sensors realize this accuracy over a really wide temperature range, whereas the NTC measures only a very accurate in the specific design small temperature range. And due to the international standardization, the PT-RTD's accuracy is recorded in tolerance classes, like for example the F.1. All right, Andreas, the stage is yours.
All right, thank you, Charlotte. Let's talk a little bit about typical applications and what is important on the property side in these applications. Here on the left side, you see a typical product, a wired RTD. This type of RTDs are ideal or designed especially for assembly into tubes and probes. Nevertheless, they also can be used in other assemblies. You see here a few of them on the pictures, and they especially provide a good thermal contact if you connect it to a planar surface. Here on the right-hand side, you see the strengths of PT-RTD Charlotte referred about, such as wide temperature range or extreme or very high or low temperatures. And I like to give you a few typical examples. We do not go into very detail because all of you have different applications. The first three ones are the traditional applications and the home turf for PT, such as exhaust gas treatment, the petrochemistry, the oil and gas area, or process monitoring and automation in productions. For that, you typically use the wide temperature range the RTDs deliver. You have high temperatures and you want to have a low signal drift and a high accuracy. The linear signal typically is not mandatory. You can always compensate that with special electronics or more complex electronics, but it definitely helps you to keep electronics simple and to have replaceability just in case you want to change the temperature sensor after a couple of years. The second field is home appliance, and in a wider sense, also application like pellet grills or pellet furnaces, which become more and more popular in the recent years. Also here, the temperature ranges are wide. You go up to a few hundred degrees C, or even up to 800–900 degrees in special pellet furnaces that are used for heating in HVAC environments. The next section, e-mobility, is quite prominent. Meanwhile, all of you know that the RTDs are used mainly in three applications there. The first one is the charger plug protection, where you want to monitor heating, especially in fast charging modules. And for example, in China, it's considered to make that mandatory for that application. And the application is really building on the low signal drift and the high accuracy and reliability of the PT-RTDs. It's also used for e-motor protection. In the past, people used KTY semiconductor sensors. Recently, the PT is taking over a lot of the share and helps to make that application reliable and to cover a wide temperature range from -50 degrees to 200 degrees or a little bit more. Medical applications are a wide field for PTD. We have, for example, the data loggers that are used to monitor the transportation of pharmaceuticals and biologicals, such as vaccines, for example. And if you go down to dry ice temperature, the PT-RTDs have a very clear signal. You can even have DNA glass at that temperature, which makes them a good product for this application. Last but not least, heater control units, where the temperature range is wide. That could be, for example, in 3D printing, it could be in e-cigarette devices, or in other consumer devices that run up to higher temperatures. Let's have a look also to the other RTD formats. Here you see our SMD types. They support pick and place mounting, which makes them good for full automated lines. They are very compact with a small footprint. And last but not least, they also are cost efficient. This type of elements are also used in e-chargers. They're widely used in data loggers and trackers. And we learned in the pandemic that they also enter into a lot of medical devices and equipment to monitor, for example, a patient's health. For the SMDs, the range is up to about 200 degrees, depending on the product. So the extreme high-low temperature capability is not as important, but in many applications, you want to have a low signal drift. You want to have the high accuracy and reliability of the PT-RTD, and the linear signal usually helps to standardize the electronics and to be in a DIN environment where you can later on have the same element with the same characteristics. One very new and prominent application is protection of electronics, and especially power electronic boards. If you think about e-mobility, you want to manage high currents and high voltages when you charge your battery or when you use your car. And then the electronic boards, they get rather hot. And we have developed a part in the special SMD that can be applied with sinter technology, and that covers the range up to 200 degrees C, which is especially tailored to this application. I will later show you a little bit more about that. Drift compensation in gas sensors and other sensors is a typical application for the SMDs. If you have a gas sensor that is temperature dependent, you need a reference, and the PT-RTD allow you to do that with a simple electronic on the same board or at an adjacent board in an integrated system. Last but not least, we have typical HVAC building automation applications. They can use the wired sensors, but they more and more use SMD types, for example, in smart thermostats, or they use what you see here. This is a SMD type sitting on a small PCB board. It has two pads on the opposite of the board. So it is made especially to simplify the assembly process for probes. You avoid shortcuts. You can put it on a very on the same position. So it helps you to reduce the cost for the tube assembly. And also it helps to make the sensor more precise, because the heat bridge here reduces the heat coming in via the wires. If you think about applications like heat and cold meters, you want to have a very precise measurement over a couple of years that fulfills even norms or legal aspects. And this product is especially optimized for that. Nevertheless, it also is helpful in probes that are used for duct and immersion sensors. Right, in the next section, Charlotte will inform you about the products and the properties, and I hand now back to Charlotte.
Right, thank you. So on the last slide, Andreas has highlighted some products and also some applications, and he also worked out the decisive properties of PT-RTDs. And in the next step, I would like now to take a closer look at some of these key properties. And I will do so by looking at our M series, which is actually the standard type for the majority of applications. All of these properties that are shown here on our data sheets, all of them, what you see here on the slides, as for example here in the middle of the slide. We've already highlighted the key properties shown here on the left, so I don't want to repeat it into detail. We already talked about the nominal resistance, the temperature and tolerance ranges, and also the temperature coefficient, and about the different options that are possible here. But the three other points on the right, I would like to point out more into detail. So let's start with the measuring current and the self-heating, because both strongly depend on each other. Yes, so very important to know is that the PT-RTD is a passive component, and therefore it has to be energized with a small measuring current. And this current can cause a self-heating error of the sensor, and the self-heating arrow obviously has a negative effect on the temperature measurement. So for this reason, we give a recommendation for the measuring current on our data sheets in order to overcome, in some degree, the self-heating effect. The graph here on the left shows the different measuring currents for the respective nominal resistance. So for example, for the PT100, we recommend a measuring current of less than 1 milliampere. So due to its higher resistance, a PT1000 would heat up faster, and therefore it must be supplied with a lower current than a PT100 element. But not only the measuring current and the resistance have an influence on the self-heating, but also does the self-heating coefficient. And this is influenced by the sensor-specific characteristics on the one hand and by the installation on the other hand. You will find a sensor-specific self-heating coefficient on our data sheets also. And this coefficient is influenced by the material, it's influenced by the design, and also by the dimensions of the chip. So just an example here, if we would compare an M310 and an M1020, obviously we have the same nominal resistance, so for example, both with a PT1000, and we apply the same current, then the smaller M310 sensor has a higher self-heating coefficient and would therefore heat up faster. Important is to know that this self-heating coefficient that you find on our datasheet is only a guide value that should serve you some orientation. But the installation conditions are clearly more decisive down here. So the installation of the sensor and the housing have a major influence on the self-heating. So you always have to consider the heat balance, and therefore the self-heating depends on the thermal contact between the sensor and the surrounding medium. All right, so the next aspect I want to look at in more detail is the so-called long-term stability. We state a typical R0 drift for an M-type sensor of 0.04% after 1,000 hours at 500 degrees Celsius. But let's have a closer look on that key property. Here are the results of a long-term storage test of our M222 PT1000 sensor chip for 1,000 hours at 500 degrees Celsius. I think maybe I should start with a first quick explanation of how such a storage test looks like. So we measure the resistance of the sensor at 0 and at 100 degrees Celsius. And then we store the sensor at 500 degrees Celsius. That is the maximum operating temperature range for that sensor for 1,000 hours. And then we carry out the same measurement again. So I mean, we determine again the resistance at 0 degrees Celsius and at 100 degrees Celsius. In each graph here down there, we see the temperature deviation in Kelvin at the y-axis here, before and after the test. And the left graph shows the long-term stability for R0, which is the resistance at 0 degrees Celsius. And the right graph here shows the long-term stability for R100, which is the resistance at 100 degrees Celsius. And the orange lines here represents the tolerance classes. So we can see directly that a clear advantage of the PT sensor compared to other technologies is its long-term stability, and it's also very small drift behavior. And as you can see in those graphs here, our sensors are typically even more stable in practice than specified in the norm, which means the deviation here lies far away and also within the tolerance limits here. Welcome to our Validation and Analyze Center. Here right behind me, you can see our test setup to determine the response time of our sensor chips and sensor probes. And here in my hands, I'm holding an M222 sensor chip. So let's see how much time this sensor takes to react to a 40 degrees Celsius water current with a velocity of 0.4 meters per second. The sensor is immersed into the heated laminar flow for a specific period of time. The response time can now be determined via the current applied to the sensor. I hope you liked our short video here. Here now you can see the results of the measurement that we just did. So the resistance change of the sensor related to the time. So after approximately 4 seconds, the sensor was dipped into the water, and in this case, the whole test took about 10 seconds. The orange bubbles here are the data we specified on the data sheets, which is the response time T05 and T09. And this lies in the range of 0.1 to 0.3 seconds. So in the video now, we've carried out the measurement with a bare chip and just to the materials in use. So just because of the platinum, the PT RTD has a very good and a fast response time. But again, this value is just a guide value, just like I explained already the slide before concerning the self-heating, because again, the installation conditions and the housing of the sensor has these are the decisive factors here. We actually addressed the whole discussion already in our latest webinar, so you will find it on our homepage if you're interested in take a closer look there. We can also carry out this measurement procedure not only for the bare chip, but also for house sensor probes and under different conditions. Enough now from my side, Andreas. The floor is yours.
Yeah, thank you, Charlotte. Let's talk a little bit about the products again. On this side, you see how we name the products for your easy orientation. Here on the left, we have our elements with lead wires. We typically show the size here in the first number. So this one have a size of 2 by 2 millimeters. For details, also look in our data sheet. Then you see the resistance. That can be 100, 500,000 ohms or other. And you see the tolerance class. The letter in front of the name indicates the temperature range. You find that here in the table below. So the H types go from minus 50 degree up to 1000 degree. The M types up to 500. And we also have a cryo line that goes down to 200 degree and up to 150 degree. For our SMD packaged parts, you see here on the right side, it's very similar. The number indicates the standard SMD package that can be 1206, 0805, or 0603. And we're also working here on a smaller version on our micro RTD. You find more information on the home page, which would come in 0.4, 0.2, or perhaps even smaller. Now let's go to the selection criteria and the theory. Here you see the selection journey that you typically do. First of all, you need to decide for a temperature range. Maybe additional with a safety margin. You need to decide for your nominal resistance. It can be a PT100, PT1000. It could even influence the wire connection. For PT100, if you want to measure very precise in industrial environments, you often need to use a 3 or 4 wire connection. The tolerance is important, which is standardized in the DIN-EN. Here, the only decision that is to be made is can you, in the housing, can you conserve a high tolerance class, such as 1/3 of dB? What needs to be considered? If you ask us, we can always help you in that discussion. And then the sensor design, the typical design is important in your environment. Should it be a leaded wire sensor? Should it be a SMD type or a TO or a different one for your application? The connection technology is of importance. We can optimize the wired elements, for example, for welding or for soldering. The SMD package parts are typically made for soldering. We do have, for your orientation, for your help, we have on our website a product selector. It's called Next Products, and it guides you through that journey. So here is a screenshot how it looks like. You can put in the temperature, the tolerance class, you can put in the resistance value, and you can search within size ranges. You can compare up to 3 elements, and you can send us a request to get a quote or to get support if you want to have individual consultants. What is not in the calculator, of course, is these 2 aspects: availability, economies of scale. That could be of importance if you really go for huge values and volumes. Think about a couple of 100,000 elements or projects that goes into the million. In this case, we always recommend you talk with your sales contact to help you to decide for the right element and to make sure that we can support your volume projects in a good way. Right, if you would not find in our selection the standard part you're looking for, we can give you customization options. That's shown on the next page. Here on the left side, you see that we can customize the element size and the substrate thickness. We even can give individual ohmic values different from PT100 or PT1000. We can offer combinations of PT loops on one element. For example, a sensor heater combination, such as a PT20 and a PT1000, that can be used for flow monitoring. We use it in-house for one of our products that is able to detect soot particles, and it gives you additional options beyond the pure temperature measuring. These modifications we can typically do if you have high volume requests. We do not talk about a couple of thousands here, we more talk about 100,000 pieces or more. So if you have this kind of projects, we are pleased if you talk to us, if we can support you with customized elements. On the right-hand side, you see what we can customize in mid and lower volumes. This is, for example, the length here of the lead wires of the element, which can be adjusted in a range of 5 to 100 millimeters. It can be made from different materials such as nickel, plated nickel, or silver, palladium, or platinum. And of course, we could add lead extensions if you want to outsource some of the things you typically do. And these are topics we can offer from, let's say, a couple of 10,000s here for the pin variations, or even in the lower thousands when we talk about lead extensions. And if this is not enough, we can even offer you protective housings. You see here an example. It's an encapsulated EC3032 with a PT1000 element inside. It operates from -50 degrees C up to 200 degrees C. Temporarily, we can go up to 250. It has an IP68 protection and a high vibration resistance, good response time. We even can offer options that a little bit faster with adjusted shapes. And this type of element is used in industrial automation, but also frequently in a lot of electric motors to protect the motor from overheat and to ensure that it's working over many years. All right, thank you for listening.
Then thanks for joining from my side, and see you soon.
Yes, thanks
Thank
for joining.
You. Have a
Bye
nice
bye.
day. Bye.